Welcome to this video. In this video I want to explain how we can put a global fitting distribution together via splicing in order to model data on insurance claims or insurance severities. So the motivation to consider the use of splicing to put a loss model together is by looking at the features of empirical insurance claim data. So the shape that we expect to see when looking at the empirical data collected on insurance claims or insurance severities is a shape like this. So that means that we have data which are skewed to the right and which possibly have a long, even heavy right tail. Right? So that implies that it is usually not so easy to find a global fitting distribution. And with global, I mean a distribution that is capable of capturing both the moderate, small to moderate losses, as well as the large, even extreme losses. So finding a global fitting distribution is typically very hard. Right? And recall, so I will say here, these are the typical small to moderate losses, the attritional losses. And here I've got the, say, large to even extreme losses. So if our goal is to put together a distribution that is capable of fitting these two phenomena, so both the small to attritional losses as well as the large to extreme losses, then splicing comes into play, and then splicing is a good idea, is a nice way to put or to glue together different distributions in order to construct such a global fit, right? Because typically if we would look at the attritional losses, we would think about a distribution like a gamma or a log normal, for instance, or an exponential or something. If we look at the larger losses, we could think of something Pareto or Pareto type distribution, right? So splicing is used to combine both. Combines different distributions fitting on different intervals and puts them together. So the splice distribution that we can define as such for a random variable y will consist of a weight p1 attributed to a distribution f1 star, where this distribution only has probability mass on a certain interval, say from 0 to c1, and we put k components together. So we can continue with this recipe, and the kth component in our splice distribution then gets a weight pk and is using the PDF fk star for losses y that are realizing or that take values in the interval, say from ck minus 1 to plus infinity, right? So the whole trick is that we put k different distributions together, where each of those star-denoted PDFs is taking all its probability mass on a certain interval. And then we give each of those PDFs a certain weight, and we make sure that all together they define a valid PDF on the interval from 0 to plus infinity. So the first thing we need to check is this a valid PDF? A valid probability density function. So in order to check this, we're going to verify that this PDF of y is taking positive values, and that if we take the integral from 0 to plus infinity, that we get the value of 1. So if we work out this integral, what you see is that we'll have to work like this. So we'll have to work with smaller intervals, because our components in the splice distribution only take values different from from 0. So this is component 1, this would be component k on certain intervals. So if I look at this integral, because f1 star is a valid, legitimate PDF, which only takes values different from 0 in the interval from 0 to c1, if I work out this integral, I'll get a value equal to 1. With the same reasoning, I'll get value equal to 1 over here. So if I put this all together, I'll get that the sum of the weights results, and of course this sum of the weights should be equal to 1 in order to make this a valid probability density function. So that is why this construction can potentially work to define a suitable, legitimate PDF. Now the question is, of course, how can you find a PDF that is only taking values different from 0 on a given interval, right? That's not so straightforward. So one way to do this is by conditioning existing distributions, loss distributions, by restricting them to take values different from 0 on a certain interval. So what I'm going to do here is I take a legitimate PDF, let's call it Fi, and I'm going to restrict this Fi on the interval, or to the interval Ci minus 1 Ci. And the way how I can do this is by working with conditional densities. So that becomes a recipe like this, which I can also rewrite as take a legitimate density Fi and divide it by the probability that this distribution is dividing by the probability that a random variable, y in this case, which is following the distribution Fi, the probability that this will only take values between or on the interval Ci minus 1 and Ci. Yeah. So that's how we can do this. And of course, this construction is then only defined for y values in between the interval Ci minus 1 and Ci. So this is what we're going to use for the building blocks in our spliced model. Yeah, that's how we can put this together. Now we're going to apply this kind of thinking on a specific example where we want to combine, or where we want to glue together an exponential distribution with a Pareto. And we're going to use the exponential for the attritional losses and the Pareto in the tail of our distribution. So if you look up the relevant densities, then your F1 will be parameterized like this, with corresponding CDF like this, right? So that is what I need to know about the exponential with parameter lambda. And then on the other hand, I've got the Pareto, so that will be F2 in this case. Here I'm going to use the following parameterization of the Pareto distribution with corresponding CDF given like this. So that's my Pareto distribution. And I will glue these two components together. So I'm going to use the exponential, let's say, for losses between 0 and a certain value C. And I'm going to use the Pareto for losses above C. And now, of course, the specific value of this C should be chosen with care. And typically you could use tools from extreme value statistics to pick this threshold C. But that's not the goal of today's video. So let's just assume that we have such a threshold C at our disposal, chosen carefully. And we want to put the splice distribution together by restricting the exponential to the interval from 0 to C, and by gluing it together with a Pareto that is restricted to the interval from C2 plus infinity. So that's what we're going to do. So the resulting spliced PDF is then defined as follows. You've got a weight P1 attributed to F1 divided by the probability that in model 1, the exponential model, our loss is going to be below a value C, and then we've got P2 times the density F2 divided by the probability that under model 2 our loss will be above C. So this specification is valid for losses y between 0 and C, and this specification is valid, second one, for losses from C to infinity. So that's the recipe that we want to put together. And of course, if you use the expressions for the density of an exponential and a Pareto, then you'll get an expression like this one for your spliced density. So this is for the y's smaller than C, and this is what you'll get for the losses that are above C. And I can simplify this second expression and reduce it to an expression that looks, or that is given as follows, right? And this is what I can use for the losses y that are above C. Now, of course, I know that this P1 and this P2, these are the weights, so they will be positive, they will sum to 0, so they will sum to 1. So what I can do is I can replace this with a weight P and 1 minus P to make sure that I satisfy this constraint of having weights that sum to 1, and of course the P should be above 0. So this is the spliced construction that I can put together. You can verify that this is a well-defined PDF so that it integrates to 1 and takes values that are positive. So to conclude, splicing is a technique that we can use to glue different distributions together and to make sure that we construct a distribution which is capable of providing us a global fitting distribution, for instance, for modeling insurance losses.